This video will be about using trigonometric substitutions to solve integrals. The first thing we'll look at is in what cases we can use trig substitution. So usually integrals involving trig substitution will be in three forms: either the square root of a squared minus x squared, or the square root of a squared plus x squared, or the square root of x squared minus a squared, where a is a constant. Now, the goal of trig substitution is to turn these expressions in terms of x into expressions in terms of theta. And the way we do this, let's look at the first case. We'll draw a right triangle. And since we have an a squared minus x squared, what we'll do is we'll put a as the hypotenuse and x as one of the legs. Then that leaves the other leg as a squared minus x squared. Now we can call this angle theta, and so we would have that x equals a sine theta. In the second case, we do something similar. We'll draw a right triangle, except instead we'll have a as one of the legs, x is the other leg, and the hypotenuse will be the square root of a squared plus x squared. And then we will have that x equals a tangent theta. Now in the last case, we have x as the hypotenuse, a as one of the legs, and x squared minus a squared. And so we have x equals a over sine theta. Let's look at an example to see how this works. So in this case, we have something in the form the square root of a squared minus x squared. So when we draw our triangle, we'll make a the hypotenuse, so that'll be 4. And then we'll make x one of the legs, and we'll have the square root of 16 minus x squared as the other leg. We'll label theta. And if we look at the graph, we'll see that the tangent of theta is equal to x over the square root of 16 minus x squared, meaning that the cotangent of theta equals the square root of 16 minus x squared over x. So our whole entire goal here is to get this to look like what we're trying to integrate. But notice that there's an extra x in the denominator, so what we have to do is say x equals 4 sine theta, and so now we can go ahead and replace and say that our integral is equal to the integral of cotangent theta divided by 4 sine theta dx. Except we need to get rid of our dx in order to be able to do our integral. So we'll take the derivative of this right here. What we get is that dx equals 4 cosine theta d theta. So we can go ahead and put that into our integral. And I'm going to rewrite cotangent theta as cosine theta over sine theta. So we'll have sine squared theta on the bottom. And then multiplying by dx, we have 4 cosine theta d theta. And so in the end, what we have is the integral of cosine squared theta over sine squared theta d theta. Now recall from the last lesson that if both of the powers of the sine and cosine are even, then you'll have to think of a special method to solve the integral. In this case, we notice that we can change cosine squared theta into 1 minus sine squared theta. Now we can split this up into two integrals. So we'll have 1 over sine squared theta minus 1 d theta. Now we should have memorized that the integral of secant squared is just tangent. So our answer ends up being tangent theta minus theta. Now all we have to do is turn this back in terms of x. If we look back at our graph, I'm going to put a copy of it here, we'll see that the tangent of theta is equal to x over the square root of 16 minus x squared. And theta, well, we said that 4 sine theta equals x, so that means that theta equals the arc sine of x over 4. So we can write that in, minus the arc sine of x over 4. And then we'll add in a plus c, and we have our final answer.